The goal of this experiment was to determine the coefficient of static friction between different objects on different surfaces. We used 3 different objects, hard plastic, cardboard, and silicone, on 2 different surfaces, cardboard and cloth. These materials are everyday objects, so we thought it would be interesting to investigate their friction. We determined the coefficient of friction by rearranging Newton's second law so that the coefficient of friction was equal to the tangent of the angle that the surface made with the ground. We used a ruler to measure the height and length of the surface since we did not have a protractor. And since we know that the tangent of the angle is equal to the opposite side over the adjacent side, we can use our measured lengths to solve for the coefficient of friction. The first step to solving this problem is to draw a free body diagram. The easiest way to do this is to align the y-axis perpendicular to the angled surface and the x-axis along the surface. The normal force of the object will then be directly positive along the y-axis, and the force due to static friction will be directly negative along the x-axis. The gravitational force will be slightly off of the y-axis since we readjusted the axes. To account for this, we will use the angle between the surface and the ground to find the x and y components of gravity. We set up this experiment so that the object is at an incline just small enough that the object does not start to accelerate down the surface, thus making our acceleration 0. Now that the free body diagram is finished, we have to apply Newton's second law to both the x and y components. The summation of the forces in the x direction is equal to the gravitational force multiplied by the sine of the angle minus the force due to the static friction. The summation of the forces in the y direction will be equal to the normal force minus the gravitational force multiplied by the cosine of the angle. Both of these components can be set to equal 0 because the object is not in motion. We know that the force due to the static friction equals the coefficient of static friction multiplied by the normal force. Also, since we know the forces in the y component are equal to 0, we can find that the normal force equals the gravitational force multiplied by the cosine of the angle. We can then plug f of g cosine theta into the x component equation to get that the force due to gravity times the sine of the angle minus the coefficient of static friction times the normal force is equal to 0. We can then set the new equation derived from the x component over the equation derived from the y component, and that leaves us with the static friction coefficient being equal to the tangent of the angle, and as I stated before, the tangent of the angle is simply equivalent to the length of the opposite side of the apparatus divided by the adjacent side. This allows us to calculate the coefficient of static friction between objects without ever being concerned about the mass. To provide a little context of all the equations that are being thrown out, a sample problem is being worked. So the calculator, which was hard plastic on cloth material, had a height of 15 centimeters and a length of 32 centimeters. Since we don't have a protractor, we couldn't find the angle, but we know that the tangent of the angle is equal to height over length. So by setting the height of 15 over the length of 32, we found that the coefficient of static friction was equal to 0.44.
In the case of hard plastic on cardboard, we found the length to be 28.5 centimeters, the height to be 9.5 centimeters, making the coefficient of static friction 0.33. and the angle 18.43 degrees. With silicon on cardboard, we found the height to be 20 centimeters, the length to be 35 centimeters, making the coefficient of static friction 0.57 and the angle 29.7 degrees. In the case of cardboard on cardboard, we found the height to be 10 centimeters, the length to be 38.5 centimeters, making the coefficient of static friction 0.26 and the angle 14.6 degrees. In the case of hard plastic on cloth, we found the height to be 15 centimeters, the length to be 32 centimeters, making the coefficient of static friction 0.44 and the angle 23.6 degrees. With silicon on cloth, we found the height to be 23 centimeters, the length to be 34 centimeters, making the coefficient of static friction 0.68 and the angle 34.2 degrees. In the case of cardboard on cloth, we found the height to be 12 centimeters, the length to be 35 centimeters, and making the coefficient of static friction 0.34 and the angle 18.8 degrees. To conclude, the cloth material generally has a higher coefficient of static friction. The cardboard has a maximum coefficient of 0.57, while the cloth material has a maximum coefficient of 0.68. This ratio of coefficients held true for all objects tested. We predicted that cardboard on cardboard would have the lowest coefficient of friction, and we were correct, with that test showing a coefficient of friction of only 0.26. We also predicted that the silicon on cloth would have the highest coefficient of friction, and were correct as that test showed a coefficient of 0.68. Thus, our understanding of materials' influences on friction is correct, because the softer materials have more surface area between the two, and the harder materials have less.